All right, good morning. I'm A.B. Gutman, as mentioned. I'm coming from Southwest Research Institute. Maybe not so close. Part of the topic that I'll be discussing is scale-up and demonstration units. Uh, so a little bit of what we're going to be covering, some of the overview of Southwest Research Institute, or otherwise known as SwRI, drivers for waste conversion, technologies that we currently have. I think we had a pretty good discussion already on that, but some additional topics of discussion, SwRI scale-up support, and of course, closing at the end, right? So SwRI is a nonprofit research organization. We have 11 facilities across the U.S. Our main headquarters is located in San Antonio, Texas, where we have about 1,500 acres of research institute and about 2.5 million square feet of labs as well as offices, and about 3,100 employees. That ranges from engineers to technicians to operators who run our pilot units as well. Our expertise is divided into 10 technical divisions, and that we're very proud to say that we do in fact cover everything from deep sea to deep space, and quite literally everything in between. Andrew and I are representing the chemical engineering department, where we have a long history of working with unconventional feedstocks, that be heavy oils, crude, biomass, municipal solid waste, specialty gases, and radioactive waste. So we definitely do a lot of work with different type of waste. So this is kind of where we land. Southwest Research Institute is located between the fundamental research, all the national labs, universities, academia, and industry. We'd like to provide that bridge that takes units from the pilot or from the lab scale to the demonstration units, pilot plants, and so that's where we excel. Some of the items that drive waste conversion are obviously socioeconomical, environmental, government imposed, and obviously the economic aspect of it. Waste is definitely something that has been addressed recently, and so it's a high topic of discussion. And so more than anything, we like to call it an opportunity, right? So U.S. landfills gather about 146 million tons of material a year that can be used. 35 million tons of that is being used in incinerators and combusted for energy. That's every single year. And obviously the U.S. is, as can be seen, it's a little bit behind compared to other European countries and Asian countries. There is a big discrepancy in that regards, but on the overall outlook, depending on which market research you go and look into, the estimated total for the globe is about 730 million tons of waste produced a year to about 2.1 billion. That's currently, and we estimate that the number will increase to 3.8 billion tons a year by the year 2050. So definitely a big driver. Now, when it comes to market, the annual growth rate on the market value for waste to energy conversion, looking at one of the more optimistic evaluations, about 11.4% an annual growth rate, currently evaluating the market at $50 billion and potentially growing up to 85 billion. So quite a sizable amount of market share. Some of the more conservative market evaluations put the annual growth rate down to about 4% annually, with a median of about 6% on growth rate. Obviously, market incentives, those are great. Those have been driving the market for renewable and waste-driven energy solutions. And so here are some of the items that we've seen. The Inflation Reduction Act definitely helped support that, especially supporting the USDA, allowing about $500 million worth of research going into the higher blends in infrastructure, as well as U.S. tax credits, 2.75 cents per kilowatt hour. Obviously, recent legislation has changed some of the timelines for that, and some projects have been put on pause for those reasons. Now, how does SwRI come into play with all this? Well, we have a patent technology. This is one of the technologies that we're working on. It is a high-pressure fluidized bed system. More than anything, it's trying to do 3 things at a time: pyrolyzing material, gasification, as well as hydroprocessing. It is a multi-catalyst bed reactor, so very, very niche in that regard. This is a joint research between Southwest Research Institute, the City of San Antonio, Municipal Waste, and as well as Mexico's Monterey Tech. Some of the goals for it are, to do some analysis on biochar, fuel product quality, techno-economic analysis, and feeding mechanisms, because that seems to be a big problem for most of solid waste. So City of San Antonio reached out to Southwest, coming into play that they were looking for biochar. So that was the reasoning why we went with a pyrolyzing unit. As you can see, it's divided into 3 sections: our partial gasification with pyrolysis, our Fischer-Tropsch synthesis, and moving up to our hydroprocessing. So doing 3 processes in 1 unit rather than having 3 separate unit operations definitely helps reduce the capital investment and unit operational cost. It comes with certain other items that I will go into play. Monterey Tech wanted to do further analysis on biochar. They wanted to see CO2 capture or sequestration, improvements to soil from the usage of it, and so that was also why they joined the venture. Now, some of the items, obviously this is a pilot unit, right? A very small, not ready for commercialization yet, but it is a unit that would be used in very high pressures, 2,000 psig, very high, specifically at those temperatures, 800 C. It's a hot wall reactor, 2-inch body fluidized bed and 1-inch riser, capable of having inlets or feedstocks that are liquid and solid, so that improves a little bit of the viability of it. It's a very robust system. It's a workhorse with it being a fluidized bed. It definitely can chug along a lot of the materials that are going to come through solid waste. And here are some of the results that we've seen. We've tested it with polyurethane and different conditions. Different pressures produce different chemicals. The gasification, I guess maybe point this out. This is 1 going through 4, just per reference if you want to take a picture of it. Temperature is a big factor as well. That wasn't part of the initial test matrix, but on later slides I'll show how some of those temperatures really do affect it. When we started with our initial catalyst, the catalyst did not really improve the deoxygenation of the material, and so that was something that we had to transition over. We tried an FCC catalyst that actually made things a little bit worse and oxygenated material even further. But after that, we landed in a method where we use sand and a nickel molybdenum catalyst, which actually helps completely reduce all the oxygen, or do full deoxygenation, almost 100%, and reduce by 50% the denitrification. So definitely we're getting there when it comes to the chemistry behind it. Obviously, this is still a 2-stage reactor, working on that 3rd stage for the Fischer-Tropsch synthesis. Now, moving over to the model feedstocks, these are the feedstocks that would be ideal in a way. We tested it with polystyrene, and then, let me go back. All right. So we tested out with polystyrene and corn stovers. As you can tell, We had a varying temperatures and as well as varying pressures. The temperatures really did have a major effect on it. As you can see right here, that styrene only went down to 41%, which is similar to here. However, the breakdown of the polymer version of polystyrene was a lot less than over here, and that's just from the compounds that we're making. We're making more toluene, cystibylene, which is kind of letting us know that we are breaking down the polystyrene. When we went down and used corn stovers, however, we started producing water, which was something that we were not anticipating. And I'll explain how that having any water in your pyrolysis unit is not ideal at all. It tends to have larger effects on the downstream, especially on the gas section. Yeah, and then we continuing on with another test, part of the test matrix. We started testing organics, and as we can see, we started, again, the temperature difference made a big difference on the cracking of the polystyrene and producing more of those toluene, benzene, acetylene type high-value chemicals that we can use for selling or whatever, downstream processes or anything like that. Once we started using recyclables, though, we started making, again, cystibylene, which basically means that we're at a high enough temperature, but we're reconstructing towards the polystyrene. So the chemistry right there, it's still a working art. Further research needs to be done, but points towards the right direction of higher temperature, more preferential selectivity. Now, going into the gas, which is the downstream section of the reactor, this is where it actually impacts a lot. As I mentioned, test number 8, which was the one with corn stover, and where we saw water production. On your pyrolysis unit, you will see large amounts of CO2 and CO production with the presence of oxygen or water. So very in line with what we saw. We can see high amounts of methane being produced comparatively downstream when using only polystyrene. And then we can also see some CO2 and CO on the downstream for syngas that could be used for syngas if we were to use organics or recyclable material. So very useful materials can be used for the downstream processes, can be burned for energy or other things like that. All right. So when it comes to technical challenges, we're asking a single unit to do a lot of items at the same time. So these are some of the current challenges that we've seen, some of the mitigation as well that we've done along with it, and obviously we've been successful in mitigating some of these challenges. However, liquid conversion is another big item that we're working on, and hence the Fischer-Tropsch synthesis is the next large step towards having a 3-in-1 type reactor that would remove the formation of oils that slow down the reaction or poison the catalyst. And so these are some of the items that we're looking moving forward. So what do we learn from all this? Obviously, new technology. We have confirmed pyrolysis and hydrodeoxygenation of the materials that we are introducing. The feedstock is being deoxygenated. We're still working on the denitrification of it. We have confirmed the impact of pressure on pyrolysis. Again, the unit can go up to 2,000 psi, so it can withstand, it can produce better material and not have just biochar being produced. We also have continuous coke formation, right? I mean, that is better than fouling the reactor. And of course, fluidization optimization and cat-oil ratio. Again, we're trying to get a fluidized bed system, so as the material runs for a longer time, some material will fall off spec, and so we'll have to address that in a different method. Now, when it comes to capital, we did a techno-economic analysis on it. A unit like this, being able to produce or process about 840 tons a day, would have a capital cost of about $20 million, with an operating cost annually of $6.2 million. Sounds like a large price tag, but looking at the per gallon cost of capital, we're looking at about $1. Some of the more bioethanol plants are a little bit higher than that at $3 per gallon per capital investment. So definitely in the right path, in the right trajectory for reducing the necessity of multi-stage systems and having it all in one system. Obviously, another big part of it would be the removal of 260,000 tons of waste a year as they'd be processed through this unit. And here's another chart that kind of goes into other scale large facilities that produce waste to fuel ratio, or waste to fuel items. Now, additional items that Southwest Research actually supports, it's our biomass to value-added products. So we can't really disclose all the items due to some of our investors, but some of the items that we do see in there are our pilot plant units. We also do general initial testing, so testing out the chemistry, doing all that work. Again, we take it all from the bench scale to the demonstration unit, and so we have to validate that this is an economical project and that it will actually be a viable option. Obviously, we're very familiar, I don't know, maybe we're not all familiar with it, but this chart right here of the methylfurfural production, very common that we see that from biomass production. So that's an item. But again, on scaling up, there are issues, and we see this very often, right? Storage, transport, and degradation, right? So transporting large amounts of biomass tends to be expensive. Energy density is very low per cost of transporting. The degradation, again, back to the energy density, humidity, water content affects the amount of energy that is being stored within the biomass and definitely affects production downstream. Obviously, there's pretreatment required, whether that's shredding the material down to smaller particles or pelletizing it to increase the densification, or if we need to do additional treatment to increase the surface area to have better reactivity. That's all part of the challenges that we see right now. And obviously, the extreme process conditions. Most of the conditions that we see with it, it's in HCl. There's toluene. Some of them are obviously they're all hazardous, but they can create even more hazardous environments, damage to equipment if not properly selected. Obviously, we need to go with more exotic alloys to be able to withstand HCl. And then, of course, slurry pumping, solid feeding, everything. Being the fact that it's solids, you're going to have more wear and tear on equipment. So that increases your unit maintenance and downtime. Having to do analysis on wear and tear, replacing pumps, that's a big item that we see on challenges. Depends on how we feed. Obviously, there's lock hopper mechanisms and everything like that, but they also see some degradation as well. All right, now for waste plastic recycling, that's another scale up that we've worked on in the past. Pyrolysis, gasification, and hydrotreating, all on plastic waste. When it comes to mixed plastics, though, that one we've done a whole demonstration unit for it, where it was designed, built, fabricated, all in-house. And some of the items with it, some of the main goals for the project was to check forms of injection. There was varying methods of injection into the reactor for the fluid bed. So that was one of the main matrix of testing to see how would that react. Also, we increased the size of the reactor to be more similar to what is in industry. And so any items that would have been for fouling or could have plugged up the reactor, everything was very much to what we'd have seen in industry. And of course, there was a lot of learnings of how material being introduced into the reactor affects it. Obviously, plastic recycling has its own set of issues, right? Whether it's solid feeding, one of the biggest items that we see is PVC, specifically with the chlorine in certain environments and in competing reactions can produce HCl, and so the downstream has to be adequate enough to be able to support some of the more extreme conditions that it produces from being there. We had to use high pressure delivery systems that included extruding material into the reactors. And obviously, this is one of the biggest, most important spots to consider, cold spots. Pumping molten plastic actually is a very interesting art more than anything. So as long as you don't have any cold spots, you'll be able to pump material easily. However, any defect or damage on insulation really does take a big toll, and it really affects the downtime. So that's something that we've seen, fouling accumulation, just pumping plastics through lines fouls up the lines faster than people are anticipating, especially on molten aspects. And of course, there's very specific design considerations for feeding mechanisms and fast delivery systems. So that is kind of what we're at. I think.
All set?
Yeah, I think that's all set.